Welcome back to Lean Together 2025. Our next speaker is Emily Riehl, who's a professor at Johns Hopkins University, and I'm very pleased to have her speaking here at our conference. And she's going to tell us about the Infinity Cosmos project, formalizing 1, 2, V, and infinity category theory in Lean.
Great. Thanks very much. So this is a report on a new Lean project that was launched this past September after I attended a talk of Pietro Montecone, who explained sort of how the whole Lean project stuff works, and with the suggestion of Johan Kamelin. Co-leads for this project are Mario Carnero and Dominic Verity, and I'm serving as the maintainer. So here's the abstract for the talk. I will say a little bit about the idea behind the Infinity Cosmos project and what infinity categories are. The aim is to formalize some infinity category theory in Lean. I'm going to try and limit the amount of time I spend giving sort of a high-level overview of sort of what we've been up to, what our progress has been so far, so I can spend some time discussing some of the challenges that we have been encountered along the way. One of the features of this project is, even though the ultimate aim is to develop infinity category theory in Lean, a lot of the formalization itself involves sort of lower dimensional category theory. So 1 category theory, 2 category theory, or enriched category theory. And we've encountered some sort of frustrations along the way, and I'm hoping folks will help us speed things up. Okay, so here's the plan for the talk. Great, so first I want to just give a little bit of orientation to the mathematics. So this is about something called infinity categories, and what on earth is that? So firstly, here's the sort of Lean definition of an ordinary 1 category in dependent type theory. So it has an underlying type of objects, then a dependent type of arrows, then the structure of identity terms and composition functions, and then some axioms. So the idea of an infinity category is that we just have to replace all of these types by infinity groupoids, which is another name for homotopy types, which is another name for anima. And what that is roughly is it's the idea of a topological, or the data of a topological space that is encoded by its homotopy groups. A thing to note about that in particular is that the homotopy groups will encode the path components of the space, but not the sort of underlying set of points. So sort of functions between infinity groupoids are a little bit complicated. Axioms about unique existence get replaced by axioms about contractibility. So this last bullet point, sort of suitably weakening all of the structure and axioms, is somewhat more complicated than you might think. And in fact, sort of mathematical on paper definitions of infinity categories don't really follow the outline that I just suggested. Instead, they introduce something that I like to describe metaphorically as coordinates, what's referred to in the literature as a model of the ideas of an infinity category. And the most famous one is something called a quasi-category. This, in fact, is in Mathlib already, and here is the definition. So what a quasi-category is it's something that's a simplicial set. A simplicial set refers to a particular type-valued functor. So it's a contravariant functor from some category index and types, satisfying this one property, which is called horn filling. If you're seeing this definition for the first time, it takes a bit to absorb, and really the point I want to make is that it's not at all clear that this connects in any way to the idea of the previous page, that this is like an ordinary category, but we've replaced all of the types by infinity groupoids. And in fact, that's a bit subtle. So sort of connecting this definition to the idea of an infinity category that sort of experts and newcomers alike prefer to think with is a bit subtle. So firstly, the sort of corresponding coordinatization of the notion of infinity groupoid is something called a Kahn complex. This is also in Mathlib, though sort of hilariously this morning I woke up to a message on the Zulip from Joël Riehl, who pointed out that the definition of Kahn complex in Mathlib was wrong. It had an incorrect sort of n equals 0 case. Fortunately, he's very quick and so fixed it. So this definition has been in Mathlib for quite a while. It has been incorrect the entire time. And I mean, the reason nobody caught this before is it essentially hasn't been used yet. So the way that I would connect the definition of a quasi-category to the idea of an infinity category would be to sort of firstly define the maximal subcomplex of a quasi-category. This is the sort of infinity groupoid of objects that replaces the type of objects in an ordinary one category. Then I can define the dependent type of arrows by using a certain pullback of this exponential. I'm using the kind of Cartesian closed structure in simplicial sets here. This would define the infinity groupoid of arrows between two objects. And then I could start thinking about composition by showing that an area composition is, there's not really a canonical composition map, but it's well defined up to a contractible space of choices. And the point of all of this is just to emphasize that none of this is in Mathlib. So even though the definition of quasi-category had been in there previously, the definition, or incorrect but now corrected definition of concomplex had been in there previously. It hadn't really been developed very far yet. And I mean, this is in progress. So, one fact, I'll mention this a little bit later. So there is a work in sort of branches of Mathlib that develops these notions more fully, but not a lot had been done there. So this is not sort of the approach that we're going to take for developing infinity category theory with the Infinity Cosmos project. We're going to do something else. And what is that? So our objective is to add not just a definition of infinity categories to Mathlib, that's there already with this notion of a concomplex, but to add the theory of infinity categories to Mathlib. So, there's a very large library of category theory in Mathlib, and the hope is that eventually we will have a parallel library of infinity category theory, because the mathematics that depends on infinity categories needs this theory as a replacement for one category theory, an extension of one category theory. And there are two approaches to this in the pen and paper literature. I like to describe them using a metaphor where one is called analytic and one is called synthetic. The analytic approach is the one that is sort of based on quasi-categories and would implement the constructions that I mentioned on the previous slide. Here we're going to do something more synthetic, or maybe more abstract, or more axiomatically, which tends to pair well with the style of Mathlib. And the idea is that we're going to develop the theory of infinity categories using an axiomatic notion of something called an infinity cosmos. And what that is it's a particular sort of enriched category whose objects are infinity categories. So the definition of an infinity cosmos is a bit complicated. I'll show that in just a minute. But the advantage of this approach is from this infinity cosmos, one can extract a two category, which plays the same role to infinity category theory as the two category of categories plays to one category theory. So this is a two category whose objects are infinity categories, whose morphisms are infinity functors, whose two cells are infinity natural transformations. And this two category does not capture all of the theory of infinity categories, but it captures sort of a large basic core. So in particular, notions of adjunctions and colimits and conextensions can be understood at this level of the two category. And some of this is in Mathlib already. So Mathlib already knows what a two category is and already knows what an adjunction inside a two category is. So once we have built this two category of infinity categories, it will know what an adjunction between infinity categories are, just as a special case of that definition. So this is why this sort of feels like a feasible project to me at sort of this stage of development of Mathlib. Now there's one caveat, which is what's in red at the bottom, which is constructing examples of infinity cosmoi are where the hard work will go. But the idea is that this is something that will be very hard, that is done once in showing that all of this abstract theory of infinity cosmoi specializes to the case of quasi-categories. That will be quite difficult, but that's something that can be done sort of once by some, brilliant experts. And then it won't be something that'll have to be done in necessarily every step of every proof. So when we extend the theory of infinity categories a little bit further, we can refer to this axiomatization rather than solve sort of homotopy coherence problems, which are come up when you're formalizing any definition sort of directly involving quasi-categories. So to get a sense of some of this hard work in proving that quasi-categories define an infinity cosmos, there's a talk by Jack McCone on Thursday about one of the important ingredients in this proof. So that is not something that we're sort of focusing on right now. And I'll talk about any more, but it's something that will have to be done to really make this theory usable. Okay, so that's sort of all I'm going to say about the plan of it. And the main takeaway is that, infinity categories are sort of complicated and scary, but really the bulk of the formalization that we are doing in this project involves one category theory, two category theory, or enriched category theory. And in terms of progress, so we launched the project in September, and the initial target was just to get a definition of an infinity cosmos formalized. So what is this definition? It's an enriched category. It's enriched over the category of quasi-categories. And then it has some class of maps called isofibrations that satisfy a bunch of axioms. The first axiom asserts the existence of various sorts of limits, but these limits are meant in an enriched sense rather than in the one categorical sense. And then the isofibrations have to satisfy various closure properties. So what our task was essentially was to add, Mathlib already knows about, of course, ordinary one categorical limits, knows about enriched categories, knows about quasi-categories. It did not know about enriched limit notions, and so that was the bulk of the work that we have completed. But now we do have a definition. So infinity cosmos is type with a structure of an ordinary one category, also the structure of a simplicity enriched category that has the property that its simplicity enriched Hom sets are quasi-categories, has a special class of isofibrations, and then these isofibrations satisfy various limits. And so that is the definition. So that's kind of our main progress report. The other progress is I was advised that it's good to send things to Mathlib that might be of general interest sort of right away. So, so the definition of an infinity cosmos is not in Mathlib, it's in our sort of lean project, but we have successfully PR'd various things that might be of more general interest, including some aspects of one category theory, a notion of co-discrete categories paralleling a notion of discrete categories, some developments in enriched category theory that I'll say a little bit more about later on, and then some developments in kind of abstract homotopy theory that are sort of related to this project. I wanted to pause here and say a little bit about some of the challenges that we've been encountering. I mean, one of them is that I think this material is quite difficult to review because the mathematics is rather specialized, and Joël Riehl has done an amazing job, but I really feel bad about the demands that we've placed upon him as a reviewer. Other challenges we faced, I think, mostly stem with my own personal failings. I think come to this with less experience in lean than would be optimal for a leader of a lean project. And, there's various times where I feel like I'm actually the bottleneck in getting anything done. So for instance, we're at a stage now that we have a working definition of an infinity cosmos where I need to expand the blueprint so we can start proving sort of lemmas about the definition and developing an example of an infinity cosmos. I'm slow to do all these things. So if folks have suggestions for things about improving the workflow with those constraints, that would be very welcome. Okay, so that was the kind of overview of the aim and the progress. I realized that was a little bit fast, but the aim of that is that I can slow down and describe at a hopefully a more understandable level some of the challenges that we've met along the way and things that I would love to have ideas about. So I'm going to illustrate with 3 case studies, one involving one category theory, one involving enriched category theory, one involving 2 category theory. And all of this stuff is in Mathlib right now. So this has all gone through the PR process, has been approved. But I'm a little bit unhappy. So let me explain the first problem. So, so over the summer, Mario and Carnero and I started doing some formalization that is meant to support the construction of the two categorical quotient of an infinity cosmos. So this is the two category whose objects are infinity categories, whose morphisms are infinity functors, and whose two cells are infinity natural transformations. This two category is still work in progress. So there's some difficult things we still need to do to complete this construction. But towards this, we introduced something called a reflexive quiver, which is an extension of the notion of a quiver. So a quiver is just a type with a dependent type of morphisms. A reflexive quiver additionally has an identity, a specified identity term in the HOM from X to X for each object X. Okay. And then what we also did is we formalized the free category and underline reflexive quiver adjunction between cat and the category of reflexive quivers. So there had been an analogous adjunction between categories and ordinary quivers. I forget who that is due to, so I won't give credit where it is due. But there's something I was a little bit unhappy about in the proof. So the way we built this adjunction is we explicitly defined the unit and the co-unit natural transformation, and then checked the triangle identities. And what I've circled are in this formalization are all the steps that I feel like are sort of unessential. So on paper, when somebody does a diagram chase, what we're checking is that some composite of arrows is equal to some other composite of arrows, and there's steps where you sort of, you essentially sort of tile your diagram. You say, well, this little bit commutes by some naturality, this commutes by some definition, this commutes by that. Those are the essential steps in the proof. But Lean was repeatedly confused by what category we're in when the objects are type classes. So both categories and reflexive quivers are types with a structure, and it would be confused about how we should think about these types and what sort of morphisms are. There are two different notations for a functor between categories in Mathlib. There's sort of the standard one that gets used, I think normally, sort of throughout most of the library, where there's sort of a special kind of arrow you write for a functor. But here, categories are objects in a category, and so we have the usual arrow or HOM notation for a functor between categories. And some of the properties we were trying to use, Lee knows about in one notation, but not the other, and vice versa. So we had to sort of continually remind Lean that identities are identities and composition are composition, either in the one category of categories or of functors, and similarly for reflexive quivers. And I don't know, I found it very annoying. This is a proof that I feel like I should have been able to write myself, because the steps are really not that complicated, but I needed a lot of help from Mario just figuring out how to tell Lean what we're doing. Also, and I'll mention this a little bit more in the two categories thing, often you're in category theory, you have some composite of morphisms is equal to some other composite of morphisms. And if you post-compose, if you want to apply that sort of under a functor, it'd be great if that were easier to do. What you have to do is sort of, it's kind of more complicated to do these rewrites than I really think it should be. There's also sort of annoyances with associativity that I can imagine would be streamlined. So anyway, these are some sort of frustrations with one categories. With enriched categories, I think the main challenge is essentially that you have to be a little bit more precise when you're formalizing than you do when you're arguing on pen and paper. So, so what is an enriched category anyway? Essentially it's a category whose HOMs are not sets, but something else, objects in some other category, perhaps a monoidal category. But there's kind of two different ways where the notion arises in the literature. So, so Peter May explained to me that this can be used as a compound noun, enriched categories, or as an adjective, where a category that has been enriched. So in the noun form, an enriched category has no pre-existing underlying ordinary category. So you would just say it has a type of objects, and between each pair of objects, it has an abelian group of HOMs, for instance. Or in the adjective form, you do start with an underlying one category, and now you want to make that specific type of morphisms the sort of underlying type of some abelian group or something with an additional structure. And this distinction between perspectives is often elided in the enriched category literature, but of course it can't be in formalization. And so Mathlib has two notions referred to in enriched categories and enriched ordinary categories, respectively. And here are the definitions. So, so an enriched category, you can see it just mirrors the definition of an ordinary category, except for these HOMs, live in some other monoidal category V as opposed to in the category of types. For an enriched ordinary category, what we're starting with is type C, which has one category structure and then has an enriched category structure. And then we have a lot of explicit equivalences expressing compatibility between this underlying one category and something that one would extract from an enriched category in the noun category form. And it's just sort of a lot to deal with. So, so we're in the process of developing more aspects of enriched category theory, and it kind of feels like we have to do everything twice, both for the enriched categories and the enriched ordinary categories. Maybe this is just how this is, but I thought this was interesting and something that we're encountering now. So the final thing I wanted to highlight is a challenge from two category theory. So we're about to enter a stage of this project where really the bulk of what we're doing is working with a two category, and it's really not entirely at all clear to me sort of how this is going to go. So, firstly, well, for various reasons, but let me try to say something concrete. So a two category has an underlying one category, but then in addition, we have these two cells. The two cells are the things that I've depicted with the double arrow here that inhabit these regions in the plane. So for instance, this alpha is a two cell whose boundary is the composite of G1 and L2. That's the source, and then the target is the composite of L1 with H1, where the things with single arrows are sort of one cells in the ordinary one category. So on paper, the way that two cells can be composed in a two category is by pasting. So what I've displayed here is an example of a pasting diagram, and this will have a unique composite which will be a two cell whose zero cell boundary is B and E, whose zero cell source is the composite R1, G1, G2, whose one cell source is the composite R1, G1, G2, and whose one cell target is the composite H1, H2, R3. And, there's some theorem that there's various ways of sort of whiskering these two cells and then vertically composing them all agree. But that's just not how this works, it seems, in Mathlib. So the two cells here each belong to dependent types over the boundary one cells and objects. And depending on how the whiskerings are encoded, they're not obviously composable at all. So if I were to compose up these two cells to get this composite, at some point I would compose a whiskered copy of eta 2 with a whiskered copy of epsilon 2, but depending on how you do these whiskerings, it's not obvious to Lean that these things are composable at all. And so in particular, in sort of an unrelated project over the summer, I added some stuff about mates in a particular two category, the two category of categories. And essentially the result that I added about mates is that this particular pasting diagram that I've displayed here reduces. So the eta 2 and the epsilon 2 are meant to be the unit and co-unit of some adjunction between L2 and R2. And so that part of the pasting diagram just disappears, gets replaced by an identity. And this whole thing simplifies. So in the theory of mates, that has some implication, which is the theorem proven here. But the proof, which is a proof that I wrote, is not the right one in my view. Firstly, this proof only applies to cat and does not apply to a general two category. The way that I would like to argue is essentially by using results about these pasting diagrams that I can compose the cells in any way that I want. What I had to do instead to get this to work at all, because of issues with these two cells belonging to dependent types that are not obviously composable, is pass to the components and then do an argument. I found this unaesthetic at the time, and the real issue is now we only have this result in cat and not in a generic two category. So I think we're going to have a lot of challenges in dealing with two categories, also in comparing the notion of two categories and cat enriched categories, both I guess in the enriched category sense and the enriched ordinary category sense. So if any of this interests you, we would love to have you come help us out. So here's a list of everyone who has contributed so far and a link to where things can be found, and I'll stop and take some questions. Thanks.